Moving. Thank you very much. So thank you for the introduction, and I'm Yong from San Jose State University. Today, I will talk about the electrical circuit and qubit interaction in superconducting qubit. The main purpose is not really about superconducting qubit. It's just to share with you how an electrical engineer can play a critical role in quantum computing. So I will first very quickly introduce my school and also my lab again. And I assume that some of you might not have the quantum computing basics. So I still want to talk about some of the basic concepts so you can appreciate why we will do something related to those basic concepts in the quantum computing architecture. And then I will talk about how the electrical circuits interact with superconducting qubit in a superconducting quantum computer and its design and also HFSS simulation. You see, this is a very profound topic, so it's almost impossible to cover it within 1 hour. But however, I would like, hopefully this will arouse your interest and that can make you spend more time in the future to study. My lab actually mostly work for semiconductor simulation from atomic state all the way to radiation simulation on SRAM. And we can also measure cryogenic temperature for semiconductor chips. And we think that in the future, your quantum computer, as passive qubit, you will see that later. We need a lot of low temperature semiconductor surrounding it. And hopefully they can work at 4.2 Kelvin to control and measure the quantum qubit. At San Jose State University, we have 26,000 students, and we are at the heart of Silicon Valley, and we are a minority serving institute. Many of our students work in the top-tier companies here in Silicon Valley. In our Master of EE program, we have a concentration on quantum information and computing, and here our philosophy is that we believe the student need to learn some basics on quantum computing and then learn the low temperature electronics and also quantum computing architecture. They probably will be well trained to work in the electrical part in a quantum computing company. At the same time, we have a Master of Quantum Technology, which it is co-host in physics and EE. This one is a 2-year program, and it has a more in-depth interdisciplinary classes on quantum computing. So that's all my advertisement for my school. But finally, as just mentioned, I do have 2 books, Introduction to Quantum Computing, which is mostly based about the algorithm, and then quantum computing architecture, in which I cover the spin qubit and also the superconducting qubit. But the main purpose is to show how they interact with a classical world. And you should be able to download them for free if your institution has a free subscription to Springer link, which probably is the case in many universities. Okay, that's all for my advertisement. Thanks for listening. And now I would like to talk about the basics of quantum computing, by assuming that you don't have the background. I think you know very well in classical computing, we need to represent the information of 0 and 1, they are binary. So it is pretty easy to represent. You can use head and tail, happy and smile, or happy and sad, or most practically, we have been using the transistor on and off to represent the state of the information. In quantum computing, if you only work in something called basis state, just like in the 3D space, you have the basis state of X hat, Y hat, Z hat. If you only work in the basis state, you also only have this 0 and 1 state. Although we write it in the Dirac bracket notation, but that is fine if you don't understand. After all, it's just talking about the state. So in principle, I can represent it by head and tail, happy and sad, and transistor with on and off. There's no difference between classical and quantum computer if you limit it to the basis state. But quantum computer is special because we are allowed to compute in the so-called superposition state. It is like we have 0 and 1 state, it can be in another state, which is a linear superposition of 0 and 1, and is scaled by the prefactor alpha and beta, which are complex number. An analogy people would like to give is just like a spinning coin on the table. You don't know whether it's head or tail. It's just like we can say it is in a superposition of head and tail. Of course, this is just an analogy. We cannot use this for quantum computing. But I hope you can appreciate that the superposition of states is what makes quantum computer so special. If it's so special, then it would be great if we know what is alpha and beta. But unfortunately, think about the spinning coin. If I want to know its state, what will you do? You need to stop it. That is a measurement. Then the coin will collapse to either head or tail. It's just like a state, a quantum state, which is alpha 0 plus beta 1. If we do the measurement, it will collapse to 0 or 1. We can never measure alpha and beta. This collapse process is completely random. And the probability you will collapse to 0 is proportional to the square of the magnitude of the corresponding coefficient. So from here, you see that quantum computing has a lot of information contained in this alpha and beta, but we cannot get it easily. So that is another property of quantum computing. Quantum computer is also special not just because of superposition, but also that it has entangled states. We won't go too deep, but basically entanglement means that if I have two states, I won't be able to factorize it. Let's look at an unentangled state first. So earlier I talked about the basis state, which was just 1 qubit. Here I'm showing 2 qubits. And by analogy, you probably can figure out this is just like head, tail, head. You have 2 bits, just like 2 bits in your classical register. But its quantum computing analogy is that the basis state will also be head, tail, head, and tail. So or 0, 0, 0, 1, 1, 0, and 1, 1. So I have 4 basis states. Again, I can have a state that is a superposition of these 4 basis states. Now, in this particular state, if you try to factorize it like what you do in elementary algebra, you can factorize it into 0 plus 1 times 0 minus 1. This is something called tensor products. We don't need to understand this now because that is not purpose of this lecture. But this tensor product tells us that if I can describe electron 1 and then electron 2 individually, I basically obtain all the information of the total system. So this state is an unentangled state. However, there are some states, for example, this one, 0, 0 plus 1, 1. No matter how you transform the coordinate, you won't be able to factorize it. This is one of the special case called the Bell state. But the important thing is that I cannot describe this combined system by individually describing 2 electrons. So there's a theory. If you try to do simulation for quantum computer, you can do it easily using classical computer to simulate the unentangled state. But you cannot do it efficiently for the entangled state. And that's why quantum computing is so special. It has superposition and it has entanglement. And that is what makes it faster than classical computer. So we understand the basic property of quantum computing. We definitely need to understand what are the gates that we use to do the computation. First, we will see it from a very high level. Basically, a state is just like is a hypercubic space. At the beginning, I say that the basis state just like the X hat, Y hat, Z hat in our 3D space. But in reality, for the quantum computing, it is not in the 3D space. It is in a space we cannot see because it's complex, right? But we can imagine that it is a space, although we cannot see, but it's still a space. We call it hyperspace. Every state is in the space. For one qubit, we can map it to something called Broad sphere. Every point on this Broad sphere is a state. So what is quantum computing? It is nothing but just to rotate the states on the Broad sphere. So very often, we use laser or microwave pulse to change the state of a qubit. Now, and then this is a quantum gate by itself already. There are some quantum gates like the NOT gate or control NOT gate, which have a classical counterpart. But there are some quantum gates that you don't have. For example, Hadamard gate. Why? For example, I apply Hadamard gate to the basis state 0. It gives me a superposition state. Think about that. In classical computing, if you have a register, you would expect it to be either at 0 or 1. It cannot be at 0 plus 1. That would be an error, right? So, but this is okay in quantum computing. So, before we move forward again, I just want to spend more time just to discuss one of the important gates called the CNOT gate or exclusive OR gate. This is something called entanglement gate. There are many entanglement gates, but you can always reduce them to the CNOT gate. So that's why we want to spend a little bit more time. We need to be able to create a CNOT gate in a quantum computing architecture. Otherwise, we cannot enjoy the benefits of having quantum computing because we said that entanglement is a very important property for quantum computing. Now, so what is an entanglement gate? It is a 2-qubit gate. Okay, so for example, here I have 2 qubits. I have A and B. In this 2 qubits, I have 4 possible bases: 0, 0, 0, 1, 1, 0, and 1, 1. So we write it as AB, means A can be 0 or B or 1, B can be 0 or 1. When I apply this exclusive OR gates to it, then the result is that the basis states will change to A and A exclusive OR B. It means that the first qubit will not change, but the second qubit will be the exclusive OR between A and B. If you remember the logic operation, exclusive OR means that if A is 0, B will not change. If A is 1, you actually apply a NOT gate to B. Right? So if you go through this carefully, you will see that basically, if the first qubit is 0, I do nothing to the second qubit. So 0, 0 is still 0, 0, 0, 1 is still 0, 1. If the first qubit is 1, I apply a NOT gate to it. So 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. Because the first qubit is 1, the second qubit becomes the negation of itself. This is just how you apply to the basis state. But if you have a superposition state, you will see the effect. And basically the effect is to swap the coefficient of gamma and delta in this operation. And this is the so-called entanglement gate. This does not create entanglement, but if we add a Hadamard gate, we'll be able to create an entangled state. Okay, so let's step back again, see what a quantum computer looks like. First of all, in a classical computer, the quantum gate is irreversible. For example, if I know the output is 1 for a LAN gate, I don't know what the input is because multiple input pair will give me the same result. But for quantum computing, if you tell me you have a CNOT gate here and what the output is, I know what the input is. That is the first thing, because it's just quantum mechanics. If you can rotate the state from one point to another, you should be able to rotate it back. Right, that is the first thing. Another thing is, what does a quantum computer look like? In classical CMOS circuits, we will have a LAN gate, NOT gate, adder, accumulator, whatever. The circuit will run from the left to right. Every gate is a pair or many transistors. So if I have a 1 trillion gate, I need to have at least 10 trillion transistors. Your chip will go up. But for quantum circuit, it is not the case. You have a qubit sitting there. It can be an electron qubit, a superconducting qubit. It's just sitting there. Then you apply a laser pulse to it because it's a quantum gate or a microwave pulse to it. You shoot a pulse to it, then the state rotates. That is the gate. So I can apply 1 trillion gates. The qubit is still there, and I still only have 1 qubit, occupy the space of 1 qubit. So usually this is the flow of time instead of space when you see a quantum circuit, right? Each of these is a gate, and this is a quantum circuit. But this is the flow of time, not the space, like in the CMOS circuit. Okay, so I have introduced the basics. For some of you might be still a little bit vague because if it is new, you won't be able to grab them right away due to the limited amount of time. But you can think about it and try to relate this to what we will talk about in the quantum computing architecture. And you can refer to the 2 books I mentioned. And I also have a YouTube video, by the way, if you are not able to find the books. So what is a quantum computer? How do we make a reasonable quantum computer? I should say it in this way. So DeVincenzo had a paper in late 1990s and talked about the 5 criteria. First, you need to have a well-characterized qubit. We already just said that we have 2 basis states, 0 and 1, and use them to form the superposition. So of course, I need to have 2 levels. But what if we have more levels? That might be a problem. We will discuss this later. Second, you should be able to initialize them with high fidelity quickly. Why? That is because in many quantum computing algorithms, we need to keep reinitializing the circuit after some measurement or just the nature of the quantum algorithm, we need to keep reinitializing the qubit. So if the initialization process, let's say, take 100 seconds, and you have 1 trillion operation. Remember the quantum gate, right? Among them may be 1 million initialization. Your quantum computer will be very slow already, right? So initialization is important. Of course, this is a quantum object. You want to make sure that it has a long decoherence time. Means that it doesn't lose its information quickly. So that between them, we can apply many gates to do the operation. This is also important if you have a quantum error correction, because if it is not long enough, you will need a lot of resources, or even based on the threshold theorem, you won't be able to do quantum error correction. 4th point is that you need to have a universal set of quantum gates. You don't want to make quantum gates for every gate. This is just like CMOS. You can decompose any circuits into a NOT gate and a OR gate, right? Or just a LAND gate or just a NOR gate. They can form any logics. Similarly, there's a theory that if you can form arbitrary 1 qubit gate plus 1 entanglement gate, then in principle, you can at least approximate any number of qubit of circuits and any quantum gate by using this set of universal quantum gate. Finally, you should be able to do the measurement easily. We just talked about measurement is basically the collapse of the wave function to 0 and 1. So we want to selectively measure the qubit. If you come up with a quantum computer and you say that whenever I do the measurement, all the qubit need to get collapsed, then it won't be a useful quantum computer. I would like to be able to selectively measure one of them. Okay, so 5 criteria. And there's a dilemma actually. If you have a long decoherence time, usually you have a long gate time. It's not difficult to understand. A long decoherence time means you don't interact with the outside world easily. If I don't interact with the outside world, I keep my states for a long time. But what is a gate again? It's a laser pulse and microwave pulse. It means you need to interact with something. And so usually if you are very arrogant, you don't interact with the outside world, it means that you will be difficult to interact with the microwave pulse and the laser pulse also, right? So when you compare quantum computing architecture, you may see some like photonic qubit might have very long decoherence time, but it also may have a long gate times. So you should find the ratio between the coherence time and the gate time to have a fairer comparison. Okay, I spent a lot of time on this slide, but I think these are the critical points I hope you will be aware of and keep tracking in the future. So we have talked about what are the criteria. Then what does a quantum computer look like? As I said, you have some very passive qubit. Therefore, some architecture, the qubit may be moving like the trap ion or even the photonic qubit. But let's just imagine that they sit on the chip, right? They are not moving. They're boring, passive. They contain the state. We will apply microwave pulse. We apply the pulse corresponding to 1 qubit, 2 qubit gate. And we also apply the pulse to read out their state. That means we need to generate the right frequency, shape, amplitude, phase, time, and duration. These are all electrical engineering. Later, you will have more, relate more to this when you see the superconducting quantum computer. And of course, we need to have a universal set of quantum gates. I won't go into detail, but basically these are two possible sets. This set refers to the rotations about the axis of the broad sphere. If you can do arbitrary rotation, these are the 1 qubit gates that is sufficient to implement the set. And then you have a control NOT gate. This whole set can implement any quantum computers, any quantum circuits or logic gate. Right. This set is other quantum gates. These are 1 qubit gates plus 2 qubit gates. Okay, so we talk about the coherence. I want to go deeper again. I said that we need to have a well-separated two-level system. But what is the separation between them? Unfortunately, for the system we have so far, they have a very tiny separation. They are only in the order of 20 micro EV. So that is very small. It corresponds to about 200 millikelvin of thermal energy. Why we do that? Because this corresponds to a frequency h bar omega of about 5 to 10 gigahertz. And that is what we can do well in electrical engineering, isn't that? We can do microwave very well at 10 gigahertz or other modulation, right? So this is the level of the qubit separation. Then we need to cool them down, because if you look at the energy versus thermal temperature, and room temperature is 26 milli EV already. It's 1,000 times higher than the qubit separation. And that's why, for example, very often in silicon qubit or the superconducting qubit, we cool it down to the dilution refrigerator, which is about 10 millikelvin. And for trap ion, we use laser cooling and sideband cooling to cool down them to millikelvin also, so that that is also for another reason to put the train of ion at the ground state of vibration. But this is also important to have a well separation of the 2 qubit in the trap ion. If not, you might lose your energy through two mechanism, like from excited state to ground state. This is the so-called T1 time, and then or superposition will lose its information. It was 0 plus 1, it becomes, you don't know whether it's 0 minus 1, 0 plus I1. And why this is important? Because we said we use superposition in computing, and we usually need the interference from the superposition to get the answer. So once you lose the phase information, you lose everything. So that's why it's very important to have a long decoherence time and to keep the state, even not to lose the phase information. Okay, so the purpose of this slide is just to remind you that we need to go to very low temperature in many quantum computers, because the thermal noise can be detrimental to the system. Okay, so that is the overview of the quantum computer. I am not going to talk about silicon qubit. I should have removed this line. But now I will go ahead to just look at very special case of this superconducting qubit. Now, if you really go in depth to quantum computing architecture, inevitably you need to spend a lot of time on math. But sometimes, right, for engineer, I would say that you just get a trustable source and you just agree with that. Otherwise, it might take you a few semesters to really understand all the basics, right? Because all we want to know is to appreciate what they are and get the know-how. And then we know as an electrical engineer how we can control the circuit. So one of this is about the quantization of the LC tank. You probably remember, or some of you heard of it, if you have taken quantum mechanics before. Simple harmonic oscillator can be quantized, right? It can be quantized into discrete level of energy. This is the same for an LC tank. For an LC tank, if you remember, this is also a simple harmonic oscillator. The just classical treatment, right? Your energy will go from inductive energy stored in the inductor goes to the capacitive energy stored as the electric field, right? And then go back to the inductive energy. So it's sinusoidal. If you look at the current will go up and then become zero and go to negative, become zero and go to plus. Same for the voltage. It has a peak and then it has top, right? So this is very similar to a mechanical simple harmonic oscillator. This is an electrical simple harmonic oscillator. So trust me, if you go through the quantization process, you will also see the same thing. But more importantly, this happens when you go to very low temperature and it becomes relevant. When it is a very low temperature, you can imagine you can only have 1 unit of energy. And by the way, this is a resonance circuit. Only one frequency can exist, the resonance frequency. That frequency, which is h bar omega, corresponds to a package of energy, or you can call it photon. Now, you may get confused. What? We are talking about microwave circuit, and now you're talking about light? No. Photon, in general, is just any electromagnetic wave. Yeah? What we can see, a short wavelength, 500 nanometer, for example. They are not microwave, but they are photon one by one. But microwave is also electromagnetic wave. So that's why very often we talk about photon in the quantized circuit. So you can imagine when we go to very low temperature, we will talk about whether we have 0 or 1 photon in this tank. Okay, and that is the quantization of LC tank. You have a 0 photon, you have h bar omega 0 times 1/2. That is due to the nature of quantum mechanics. You have some ground state energy. You have 1 photon, then you have 1 plus 1/2 times h bar omega. You can imagine if I have 1,000 photon, I can ignore 1/2. Now I go to the classical regime. So I have an n h bar omega. That makes sense to us now, right? More photon, I have more energy. Anyway, the final thing we got is that if I quantize circuits, I do have discrete level of energy in this circuit, just like what we had in simple mechanical oscillator. But in simple mechanical oscillator, we have the so-called momentum and position in this energy diagram. But here we have the so-called generalized momentum, which is the charge stored in the capacitor, and the generalized position, which is the flux stored in the inductor. Okay, and so they will go back and forth, and then okay, sorry, I have some problem with my mute. But what is the problem here? The problem is that you see that I have multiple levels. And from 0 to 1, the energy is same as from 1 to 0. Okay, so remember what is a quantum gate? It is a laser pulse or a microwave pulse. So if I apply a pulse to 0 state, it will bring me to the 1 state. If I further apply a pulse to the 1 state, it might not go back to the 0 state. It might go to the 2 state. then that is a problem. Because we say that we need to have a well-defined two-level system. Now, it will bring me outside of this two-level. Then it won't be a good quantum computer also already. So message is here. I show that to form a qubit, to store a qubit is very easy by just using an LC tank. But however, this one is not a good quantum computer. But we can continue to work on that, because what we see there is the reason we have equal spacing is because we have a parabolic potential. Or it's due to the linear nature of this inductor. If we are able to create a non-linear inductor, then we might be able to solve this problem. Okay? So before that, let me just digress a little bit to talk about the superconducting, because we need to introduce something called Josephson junction. If we cool down the metal, eventually the electron will pair together and they become a Cooper pair. I won't spend time to discuss why or even intuitively, but the point is that now they become a spin zero ensemble or particle. Then they are no longer fermion, they are boson. Boson are just light, just like the light or photon. In photon, we can create laser because all the photons have exactly the same state, same phase, same wavelength, same direction. They run coherently like a marching army. When we cool down the metal to superconducting, they form Cooper pairs, and this Cooper pair also have exactly the same state, so they become a macroscopic quantum object. They have the same phase, and that's why we can describe them with an ensemble wave function. So what's so special? So there's something called Josephson junction. Look at this. This is just a metal, insulator metal. So this is just what? A capacitor. So when we cool it down to very low temperature, aluminum becomes superconductor. It's still a capacitor, but the superconductor is superconducting. Then it has some special property. This is superconducting. So it becomes, all the electrons become Cooper pairs. So I can describe this state, this metal by this wave function with a phase, because it's a macroscopic quantum object. Similarly, I can describe the bottom metal with another phase, phi b, right? This is a cross section. You see this aluminum, oxide, aluminum. And this is thin enough, so these two quantum objects will talk to each other and link to each other through tunneling. And we have the Josephson junction equation. We won't go into detail because of time. But these two equations bring us something very important. This one has an inductance, and this inductance depends on the cosine of the phase, which means that this is no longer a linear inductance. It is a non-linear inductance. That is the only thing I want to talk here. Okay? Josephson junction give us a non-linear inductor, right? For the details, you can Google or read my book. Now we have a non-linear inductor. We replace the inductor of the LC10 by this Josephson junction. Now, this is the symbol of the Josephson junction. It can be decomposed further into a cross and a capacitor. That cross represents this equation, the bare Josephson junction. Why do we have a capacitor in parallel? Because by nature, it is just a capacitor, metal, oxide, metal, right? So to model it, it actually has a series capacitor. Because of this, instead of having a parabolic potential energy or the energy associated with the magnetic field, just want to remind you that this magnetic field is related to the potential energy in classical simple mechanical simple harmonic oscillator. Now we actually have a sinusoidal potential energy because of this term. And with this, then the separation or the quantization of the energy becomes different. Now, the energy difference between the first two levels is different from the energy difference between the next two levels. So if I apply a microwave pulse of this frequency, it will bring the qubit to here. Apply another one, you will bring it back because this energy doesn't match the energy we apply. The energy difference between these two levels is called the anharmonicity. So that's why we need Josephson junction to build a qubit that have the right anharmonicity. Now, we forgot to mention how it carries the information. But we did say that, the bottom state is 0, the second state is 1. So remember what is 0, this energy correspond to? It corresponds to n equals 0, means no photon. And what is 1 correspond to? It corresponds to n equals 1, means 1 photon. So now we're in quantum regime, we're talking about whether your LC tank, although replaced by the Josephson junction, has 0 or 1 photon. That is the basis state. In general, it's a superposition of 0 and 1 photon, right? That is the beauty about quantum mechanics. It's just like saying that I have 1 water molecule or no water molecule in my cup, or it's just a superposition of it, right? So that is how we store the information, and that is one of the way. But however, this is not what we want. Okay, why? Because the regular Josephson junction has very bad charge sensitivity. It is very sensitive to the noise outside of the world. So why? So let's take a look. For example, this is again the qubit we just discussed. We have a Josephson junction. We also have this is the Josephson junction here, and this is the capacitor in parallel with it. Now, before we add this capacitor, I have a tiny capacitor, and I couple this system. This is a coupling capacitor to a voltage. Then it will create some background charge, Ng. Now here we plot the energy separation. I normalize the ground state, and this is the first excited state. So this is E10. You see that when there's no background charge, the energy separation between 0 and 1 is this much. And when there is an energy background charge of 0.5, the separation is this much. Then it means the qubit energy change a lot. And basically, it means that your gate pulse is not going to work in that sense, right? Because now you change the energy separation. If you have a noise due to the environment, you cannot stop your Josephson junction, your qubit from coupling to the environment because capacitance is everywhere, right? So that is not good. Okay, and this is the charge qubit that we have been talking about, talking before, and that's a problem. But what can we do? So people come up with something called transmon qubit. You add a large capacitors here in parallel, a shunt capacitor. We already shown this here, but we assume this is small or this is just a general case. But when we really talk about transmon qubit, you need to have a capacitor in parallel and it need to be large enough. With this, now you see that when I have a large enough capacitor, so my capacitive energy is smaller than the inductive energy. Now I becomes insensitive to the background charge. And this is what Google, IBM have been using in their quantum computer, which is the transmon qubit. Okay, so we spent quite a lot of time to talk about the basics of two-level. Now we need to fulfill other criteria. How about the single qubit gate? Again, there are lots of physics, and we won't go into details, right? I only show you a few how it works. First of all, we talk about the Bloch sphere. I mentioned that every state, every single qubit state can be mapped to the Bloch sphere. And a quantum gate then, of course, is just to rotate the qubit on the Bloch sphere because a computation is to move from one state to another state. So it's the rotation on the Bloch sphere. Now, in order to rotate it, turn out that you can use Euler decomposition. For any rotation, you can rotate it about this z-axis. and then y-axis, and then z-axis again. You just rotate it 3 times. You can also rotate about x and y. Okay, let's imagine I come from San Francisco to New Delhi. I can take the shortest flight, but I also can just move to through the latitude and longitude 2 times to go from San Francisco to New Delhi, right? So it's easy to understand. So that's why any rotation we can decompose in these 3 rotations. And we won't go into the math. I only want to point out one thing. This rotation, you get the rotation matrix because we have a Hamiltonian, a physics, right? An energy landscape proportional to something called sigma H, sigma Y, sigma C. We did not discuss this. This is something called Pauli matrix. And in physics, if you try to calculate the Hamiltonian, when you calculate the interaction between the microwave pulse and the qubit, you hope that hopefully we can get a term of sigma X, sigma Y, sigma C. If I can get that, then it means I will be able to rotate about this axis. That's the first thing. So how do we do that? Again, this is the transmon qubit. This is the Josephson junction. This is the shunt capacitor. We couple it to a pulse. To a voltage source. Now, this is completely classical, right? You generate a voltage source with an envelope function, S of t, at a certain frequency. If you go through the math, you find that the Hamiltonian has a sigma c term. It also has an omega r and sigma y. And we just said that if you get a sigma y term, you will be able to rotate about the y-axis. If you have sigma c, you will be able to rotate about the z-axis. So I just need to make this coefficient correct. Then I can do whatever rotation I want. And let's take a look what they are. I have omega r, fine. But what is this? Hey, it depends just on the wave, the envelope I generated. It depends on the capacitor I put on my circuit. It also depends on phi. And what are these? This phi is just the initial phase of the pulse. Right? So from here, I hope that you get the sense that I can do a 1 qubit operation by just applying the correct envelope function, the correct frequency, and correct phase from this voltage source. To make it more specific, I just want to tell you that usually we work in the so-called rotating frame and use the so-called rotating wave approximation. We won't be able to go into detail because it involves a lot of math, but in my book, I really go through step by step. I hope that it will be clear, right? But when we work in this rotating frame, it becomes even clearer what we are doing. The Hamiltonian becomes a constant times sigma x, a constant q times sigma y. And these are so-called in-phase and quadrature components. And what are they? They are cosine phi and sine phi. Again, I control how much it rotates about x and about y by changing the phase of my electrical signal. And that's how we achieve 1 qubit gate. You can imagine 2 qubit gates will be more complicated. And again, we won't go into details for the math. But how do we achieve 2 qubit gates? We have 2 qubits. Josephson junction shunt capacitor, so this is 1 qubit. It has its own resonant frequency. This one has its own resonant frequency. They couple through a capacitor. They have different resonant frequency. They don't talk to each other. They don't affect each other. However, when I want to make them to talk to each other, I apply a flux through this so-called flux tunable transmon qubit. Just take it for granted, apply some magnetic flux, then the qubit frequency will be brought to resonance to be same as this one. Then they will start talk to each other. If you derive it, again, you will see this sigma x, sigma y, Pauli matrix. You go through them. The important thing is that you turn on this coupling for a given amount of time. Then you will get an entanglement gate. Now you get confused. This is not CNOT gate, right? This is ICE-WOG gate. It's still an entanglement gate because if you try to add other 1 qubit gates to it, it is equivalent to a control NOT gate. So the main message here is that different quantum computing architecture have different native entanglement gates because they have different physics. Right? Turn out that for the transmon system we have here, building ice-swap gate is easier because we're building it based on their physics. If it's a silicon spin qubit, something called control phase shift gate will be easier. So you just add some 1 qubit gate, you can always get the equivalent C0 gate, and then you can build any quantum circuit. I'm a little bit fast. I say many things. The message to take back for this part is, again, I hope you appreciate that all the 1 qubit gates or 2 qubit gates control completely by the phase, the frequency, the envelope function of your classical electrical signal. And the capacitance you design also control the quantum circuit property. And that's it. Okay, so the final part of this talk is now I want to go to more details about how we operate and design a quantum superconducting quantum system. So now I hope you can appreciate this talk is FPGA, Python programming, arbitrary waveform generator. All of you have or going to take this class in your degree, right? High-speed electronics, digital signal processing, what else? Error programming, microwave circuit. You create the pulse you want, you go through the mixer and local oscillator to bring it to high frequency. Then you go through attenuator because you are at room temperature. We cannot bring this at low temperature. You don't want to bring the thermal noise to the bottom. And this will then go to a resonator which couple with the qubit, and then it interact with the qubit either as a 1 qubit pulse, 1 qubit gate or 2 qubit gate, or we might want to read it, try to measure the transmission pulse, then we go through the amplification, do the down conversion, analyze the signal, and then we know what the state is. And that is everything about a quantum computer. So you see that everything above here, even including this resonator, what an electrical engineer does, right? Only the qubit and the quantum amplifier is completely quantum. So we talk about the 1 qubit gate. Don't need to worry about the equation, but I mentioned to you that we need to generate the correct I and Q, right? And generate the correct signal. So what we do is just use arbitrary waveform generator in the megahertz regime. We generate this pulse. And then we just use a local oscillator and phase shift. Through this so-called IQ mixer together, we will be able to generate the pulse. This is in gigahertz, let's say 5 gigahertz, and send it to our quantum computer to do 1 qubit oscillation. So any of you who have taken microwave pulse doesn't need to understand quantum computer to understand this circuit, and you're ready to serve as long as you understand how you interact with the qubit. How do we do the read out? How do we read out the circuit? So usually we will couple a resonator to a qubit. So how does it do? So if we shoot a microwave pulse from the left, it won't go through unless your frequency is at the resonance frequency, right? Now, so you will expect a dip or you expect a peak, right, at the output if your frequency is at the resonance. Now, if you couple the qubit to the resonance, there's something called cross cut. The qubit state, whether it's 0 or 1, is going to change the resonant frequency of the resonator. And that is how you detect the state of the qubit. For example, here I plot the transmission S21 means from here to here. As I said earlier, if you are not at the resonant frequency, you have a very small S21. When you are at resonant frequency, you get a peak. Now, because of the cross cut, when your qubit is at excited state, let's say 1, your resonance frequency shift to the left. When it is 1 state, let's say 0, it shift to the right. So by measuring its resonant frequency, I will know whether the qubit is at 0 or 1. But you cannot just measure its magnitude because you see that if I just measure the magnitude at the resonant frequency, they both give me the same answer. Rather, we will measure the phase. For example, here we show the imaginary and the real part at this point. And you will see that if it is a ground state, I will get a positive number for the real part. I actually forgot which one is which, right? And then I will get a negative number if it is one state. But anyway, real divided by imaginary give you the phase, right? The message is that I'm going to measure the phase of the transmitted pulse. Again, purely microwave engineering. So I can plot it here, right? I plot in the the complex plane. I get a negative real part. Then I know it's one state, excited state. Or if I get a positive, it's ground state. Usually we'll transform it so it becomes something called IQ plane in phase and quadrature, right? But it is not a point, it is actually a block because of the noise. And that's why we need to design our circuits so that they have enough separation. If there's no enough separation, when you measure a point you got at here, then you don't know whether it is ground or excited state. If you get here, you don't know either. Because we assume that whenever we get positive, it is excited. Whenever we got negative, it is ground. You can have a demodulation circuit. Here, I just show you the math. It's just like what we did for IQ mixer earlier, right? We also need to ensure that we have the right amplification. And by using Fick's law, the important thing is that we need to have a small noise to signal a small noise figure at the first amplification chain. That's why we use something called a quantum amplifier. The quantum amplifier adds the least noise to the circuit, okay? And then after that, you can have amplification at 4 Kelvin by using ham and then further in the room temperature. Okay, I think I'm running out of time, but still just 2 more minutes just to say, then how do we design the circuit? Now you see that if I don't say that this is a quantum circuit, probably this is the same circuit you design in your microwave class. Right? This is it will be done by HFS to do the simulation. This is a Fick-9 coplanar waveguide. We try to read the qubit, so we shoot a pulse here, and they are connected to resonator. This resonator is coupled to the qubit, right? So based on the state of the qubit, then it will change the resonance frequency. You see a 2 big plane, probably you understand already. This is just a capacitor. And then it's shunt with the qubit here, so it becomes a transmon qubit, right? And then you have this 1 qubit gate that is coupled to the capacitor. Then you can do some tuning. That you can do the 1 qubit gate, right? And this is the layout. If you cut here, you see that these are just high resistive silicon substrate with niobium here, with this gap, etc. And so you need to decide the energy in the right way, right? I won't go into details, but again, you see all these criteria depends on the capacitance, on the critical current, which is the Josephson junction critical current, before which it becomes long superconductive, but this is related to the thickness and the material or the area of your Josephson junction, actually the area, right, etc. So these are all circuit design parameters to design how your circuit will operate. And this is the Fick-9, how you design the resonator. It's just a λ/4 quarter wavelength resonator, right? And then you do HFS simulation to make sure the eigenmode they are right at the right frequency. You see the qubit frequency is different from the resonator frequency, right? And eventually do something called energy participation ratio simulation to understand the cross curve I just mentioned, how much it changed the resonance frequency. You can refer to this paper, right? I do have some resources. You can go to my YouTube channel and tell you how to do a quantum chip simulation using HFSS. Okay, and that's all for my presentation.